All right, welcome brave coders. Today, we're going to demystify one of the most flexible data structures out there, the doubly linked list. Look, if you've ever felt like your data was kind of stuck on a one-way street, well, you are in for a serious treat.
So first up, let's set the stage. Let's talk about the problem we're trying to solve. You see, a lot of common data structures, they only let you move in one direction. And that can be, well, incredibly limiting when you really need flexibility with your data.
I mean, you've been there, right? It's a classic frustration. You're moving along your list, node by node, and then it hits you. You need to go back just to check a value you just passed. But you can't. You're completely stuck on this digital one-way street, and the only way to get back is to go all the way to the start and begin again.
Ugh.
And this comparison just nails it. A singly linked list is exactly that one-way alley. You can only move forward. But the doubly linked list? That's our two-way street. It gives us the freedom to move forwards and backwards, opening up a whole new world of possibilities. And that brings us to the hero of our story today, the doubly linked list. This is the elegant solution that takes our restrictive little alleyway and transforms it into a super efficient two-way data highway.
I just love this analogy. It perfectly captures the vibe of this data structure, doesn't it? It's not some boring single-file line. No, it's a full-on party where every piece of data can move freely, forwards, backwards, interacting with its neighbors on both sides. Okay, so let's get a little more formal for a second. A doubly linked list is made up of these elements we call nodes. Each node is a package deal. It holds three things: the actual data you care about, a pointer to the next node, and, this is the secret sauce, a pointer back to the previous node. And this breaks down the anatomy perfectly. In the middle, you have your data. The next pointer, well, that's pretty standard in linked lists. It lets you move forward. But that prev pointer, that is the superpower. It's the key ingredient that makes two-way travel possible. All right, that's enough theory. Theory is great, but let's see how this thing actually works. It's time to get our hands dirty and dive into some code to see how we build this structure ourselves. So in Python, the node class is actually way simpler than you might think. We kick it off with some data, and then we create our three key attributes: data, prev, and next. And notice, prev and next both start out as none. That just means they aren't pointing to anything yet. Our new node is basically an island, just waiting to be connected.
And here's how they link up. The next pointer of one node points forward to the next one in line, and the prev pointer of that node points right back. It's a perfect two-way handshake. Also, see the none values at the ends? The very first node's prev is none, and the very last node's next is none. That's how our list knows where it starts and stops.
So let's walk through adding a new node to the end. First, we create our new node. Then we handle a quick edge case. If the list is empty, we just make this the head and we're done. But if it's not empty, we travel all the way to the end. And now for the magic. It's all in these last two lines. First, we tell the old last node, hey, your next pointer now points to this new node. Then we tell our new node, and your prev pointer points back to that old last node. It's that two-part connection that creates the solid two-way link.
And the payoff for all that careful pointer management? It's huge. You get true bidirectional traversal. We can move forward or backward through our data with total ease. Just pause for a second and think about the possibilities that opens up. It is a fundamental shift in how we can play with our data.
But look, like any tool in a programmer's toolbox, it's not perfect for every single job. So let's have a real talk about the trade-offs, the powers and the pitfalls, so you know exactly when a doubly linked list is the right tool to reach for.
So here's the breakdown. The advantages are pretty clear. You get that awesome two-way travel, super efficient insertions and deletions, and it's a piece of cake to reverse. But on the flip side, that extra prev pointer, yeah, that uses more memory. And the implementation is a bit more complex, because you have to manage two pointers for every single operation, not just one.
Okay, but what's the question every developer really cares about? Performance. How fast is this thing really? Let's get a little nerdy and break down the time complexity.
Now this is where it gets really interesting. Accessing a random element is O of n, meaning the time it takes grows with the list size. Makes sense. But look at insertion and deletion at the beginning or end. It's O of 1, or constant time. That means it takes the same tiny amount of time whether your list has 10 items or 10 times million. That is unbelievably fast and a huge performance win. So we have the theory, the code, and we know it's incredibly fast for certain things, but what does that actually mean? Now that we understand the engine, let's see where this two-way street shows up in the programs we use every single day. Ever use the back and forward buttons in your web browser? That's a doubly linked list right there, tracking your history. Skip to the previous song in your music player? Doubly linked list. And what about hitting undo or redo in a text editor? You guessed it. This structure is the invisible hero behind any feature that needs to move forwards and backwards through a sequence of things.
So, the power of moving both ways is now in your hands. The real question is, what are you going to do with it? Where in your own projects will you replace a restrictive one-way alley with a high-speed two-way street? Something to think about. Thanks for tuning in.